Hello and welcome to this episode about optimization. Now, optimization is basically the workhorse for data mining and machine learning methods. I think there could be made an argument that most of the advancements we had in the last years are mainly due to the optimization techniques which have been developed and which can handle large-scale data. So if you really want to get to the core of the methods, then you have to have a look at the optimization method which is used. Typically, the workflow is such that you have given a problem, maybe by a company or somebody like your supervisor or whoever, and then you have to grasp the problem. So like, what is it actually he or she is looking for, and how could we approach this task? Like, what is the learning objective there? And then the next step is to convert this intuitive idea about learning something from your data into a formal objective, which is an optimization objective in most cases. And for these optimization objectives, we have several approaches we can use to optimize these objectives. And these approaches we will discuss here. Okay, let's start. So I have here this very generic picture of a mountain. You can imagine this like the landscape of your function, and you want to find the valley, basically. You are somewhere on the mountain and you just want to go down. That is mostly the objective of optimization. And the first optimization problem we discussed is the unconstrained optimization problem. So there we are given one objective function f, which is called the objective function, and then the task to minimize f for all the points in its domain r to the power of n is the objective. And then if we have found the argument which minimizes our function, then we call it a minimizer, and the value which is attained at the minimizer is called the minimum. Now, what you might remember from school are local and global minimas, and how you did this for one-dimensional functions. So if your function maps from the real values to the real values. Now then, for example, we have here this exemplary function on the left, and then you see that we have here two minimizers. The point on the left, x equal to -2, is the global minimizer. The function attains its smallest value at this point. And the point on the right, x3 equal to 1, is the local minimizer. So if you go from x3 now a bit to the left and to the right, then you see that the function value is increasing. But if you go further to the left, for example, then you see that the function value is again then decreasing, and hence it's only a local minimizer. For notation, we have here a global minimizer, which is a vector x star, which is the value at which the function attains its smallest function value. Note that this entity of a global minimizer is not always existent. So for example, just take a linear function, then there is not one point at which the lowest function value is attained. A local minimizer is a vector which is minimizing the function value within a neighborhood. So here we have this neighborhood n epsilon from x0, which is just the ball around x0. So it's a ball with radius epsilon around x0. So for example, this would be here the neighborhood with respect to some epsilon from x3. Okay. How can we solve now an unconstrained optimization problem? And we do that, as you probably know from school, with the first order necessary condition and the second order necessary condition. So what you have probably done in school is to just set your gradient equal to 0 to find the minimizer candidates. Why did you do that? Because every local minimizer also has to be a stationary point. Stationary point means that the gradient is 0, so if you look here at the function, then these local minimas, we actually have a derivative which is equal to 0. So the derivative is the slope you have here when you make a linearization at this particular point. So here at the left we have a very negative slope, it's very steeply decreasing. But at a minimum, we have a decrease from the left and we have an increase to the right, and in between the decrease has to be 0. But the same also holds for maxima, like here. There we have an increase from the left and a decrease to the right, but in between is also 0. But if we have a local minimum, then it has to be also a stationary point. Now let's look at this example here. So we have here defined a function f, and then we calculate the gradient and the second derivative, and then we put the gradient equal to 0, and then we get here our set of candidate minimizers. So these are here all the stationary points. Now the question is, which of these candidate minimizers are actually local minimizers, and therefore we check the second order sufficient condition. There we have a look at the second derivative, and then we check if it's larger or equal to 0. So the second order derivative is the gradient of the gradient, or like the derivative of the derivative. If you look here at the minimum, then we have here a decrease from the left and an increase to the right. And then the second order derivative reflects exactly this. So the curvature is in this case positive, or the second derivative is positive, because the slope is increasing. Here we have a negative slope and here we have a positive slope, and it's increasing all the way here. And for maximum it's actually the opposite, so there the curvature is negative. Let's just do this. So we insert our possible minimizers here in the second derivative, and then we check the value, and then we see here that for the left and the right possible minimizers we have a positive curvature, and then we conclude that we have local minimizers x1 and x3 actually equal to 3. Now what this example is not covering is the case where the second order derivative returns 0. And in this case we don't know if we actually have a local minimum or a local maximum, or maybe a saddle point. So if the second order derivative is equal to 0, then that means that at the particular point the slope is neither decreasing or decreasing. So the possible cases in which this might arrive is, for example, if you have a U-shaped function, and then here at the left and at the right the curvature is actually neither increasing nor decreasing, but the same might happen for a maximum, and this is why we can actually not say anything at this point if the second order derivative is equal to 0. And what could also happen is that you have here a very flat saddle point, just to keep this in mind. Okay, so this is what we know from school, or maybe from Calculus 1. What happens now in higher dimensions? So we will not work in one-dimensional functions. This is not very interesting. But most of the times we have a lot of features, and hence we will have a function which maps from our feature space to the real values, and the real values are then something like a loss function or a cost function, something which tells us which good our solution is in a measurable way. Now, the derivative of a function which maps from a vector space to the real numbers is given by its partial derivatives. And the partial derivatives are noted here. Very important here for this lecture is the definition of the gradient. The definition of the Jacobian is mentioned here for completeness. It's basically the transpose of the gradient, but most of the times we will work with the gradient. And if we have a function which maps from a d-dimensional space to one-dimensional space, then the gradient has the same dimensionality like the input space. So it's a d-dimensional vector, and in every entry of this vector we have the partial derivative. And with the partial derivative we just keep all of the other dimensionalities, like if we have the partial derivative subject to x1, then we treat all the values of x2 until xd as constants, and we just build a one-dimensional derivative, just like we've seen in this example before, with respect to x1. And we do this subject to every coordinate, and then we gather all these values in our gradient. Now, what we have done in the one-dimensional case can be generalized to the higher dimensional case, And the first order necessary condition and the second order necessary conditions also exist subject to gradients. So the first order necessary condition for higher dimensional functions looks like stated here. So if we have a local minimizer x from our function, which maps from a d-dimensional space to the real numbers, and f is continuously differentiable in an open neighborhood of x, then the gradient is equal to 0. And a vector x is called stationary point if the gradient is equal to 0. So what we do here is we substitute now the derivative we had for one-dimensional functions with the gradient, but the concept is the same. So every minimum, even in higher dimensions, has to be a stationary point. And similar, we have a second order necessary condition even for the higher dimensional case. Now we introduce here the second order derivative, which is the second order gradient, which is also called the Hessian, which has to be continuous in an open neighborhood of x. And then the second order necessary condition for a local minimizer is that the gradient is equal to 0 and the Hessian is positive semi-definite. Positive semi-definite, we did not have this yet. It says that a matrix is positive semi-definite if for any vector x we have that x transpose times ax is larger than or equal to 0. Let's go through an example. So the Rosenberg function is somewhat interesting because it's actually quite hard to optimize with numerical optimization, which we will see later. But it's easy to get the minimum directly in an analytical way with the first order necessary condition and the second order necessary condition. So the Rosenberg function maps from a two-dimensional space. You see here we have the axes y and x to the real values. Let's have a look at the function value. So the Rosenberg function is given by this term here. And if we now want to determine the local minimizers of this function, then we apply now the first order necessary condition and the second order necessary condition. So for the first order necessary condition, we need the gradient and we have to set it to 0. Now the gradient is denoted here. It would be a good exercise for you to compute this gradient now by the definition of the partial gradients. If you get stuck, just have a look at the accompanying math PDF, so to speak, where I have outlined these steps more in detail. So, and if we set this gradient then to 0, so this is the vector 0, so the first term here has to be 0 and the second term has to be 0. And then we have a system of not linear equations but of equations, which we can actually quite easily solve. How to do that is also written down in the math PDF. And then we get here one candidate for our local minimizers, which is the point x equal to 1 and 1. So according to FONC, we have here now one stationary point. That means that we have one local minimizer candidate at this point. Actually, if we have now a look at the objective function f, then we see that the function f is always non-negative because it is a sum of quadratic terms, so we cannot become negative. And if we insert now our point x0 into f, then we see that the outcome of f at x0 is actually equal to 0. So that means that we have found here our global minimum. The function cannot be larger than or equal to 0. And for the point x0, it is equal to 0. So all other points are larger than or equal to 0. So this means that we already know that this is the global minimum, but just for the sake of this example, we can also check the second order necessary condition. So here we compute the Hessian function of f at this point x0. How this is done you can look up in the math PDF, and then we insert in the Hessian our point x0, and then we get this matrix here. And then we can check the definition of positive definiteness. So we take any vector x which has the coordinates x1 and x2, and if we multiply this term here, then we get this term. And this again is a sum of quadratic terms, so it's actually always larger than or equal to 0. So the Hessian is positive semi-definite, and our point, our candidate point, satisfies the second order necessary condition for a local minimizer of f. Okay, nice. So finding local minimizers is not a big deal. if we have an unconstrained objective with an objective function which is twice continuously differable. So what happens if we have now some constraints? But this is then discussed in the second part of this lecture. So see you then.